Alrighty, welcome back to operating systems. So today, second last content you need for the final. So this lecture will be short. So since this lecture will be short again, you can spend the rest of the time work on Lab 6 that you've all already definitely started, yes? Yes. And you can fill out the course evaluations. So that would be great because my salary is directly tied to the course evaluations. So I would appreciate you filling them out. And I would like to still be employed. So fill them out if they're nice. So I'm still employed. If you want me to teach another course again, please fill them out. Because I am also up for review soon-ish, so they are important. So please fill them out. All right, so with that in mind, let's see what record we can do to do this lecture. So the important thing for the exam will be the buddy allocator part. The slab part has to do with Lab 6. If you've started that, it should look somewhat familiar. So what's a buddy allocator? So we left off talking about dynamic memory allocation if you were the one unfortunate enough to have to implement malloc or something like malloc. Well, just divide memory. We could bring them into keep track of a whole bunch of free blocks, have a linked list of all the free blocks, figure out which one we use for an allocation. That works. It's general. Doesn't suffer from any internal fragmentation or anything like that because you always give back memory the exact size of the request. So the buddy allocator, it restricts the problem a little bit. Typically, especially if you're the kernel, mostly for programming, allocation requests will be powers of 2 anyways, like 2, 4 bytes, 8 bytes, 16 bytes, 32 bytes, maybe the size of a page. So what the buddy allocator does is restrict allocations to only be powers of 2, at least internally, for a more efficient implementation. And how this will work is we start off managing a huge block of memory, and we'll just split it into blocks of 2 until we can handle the request. And looks a bit recursive, and we want to be able to do that because we want to have faster searching and merging. We don't want our worst case to be searching every single block in the free list. So how we implement this is we have multiple lists. So if we restrict allocation requests to be 2 to the k, so some power of 2, for 0 all the way up to end, we can round up the allocation request if needed. So therefore, our allocation, we're going to use a separate free list for each power of 2. And that way, we only have to check whether or not there's an element in the free list or not, because everything will be the exact same size. So we need 1 for every power of 2, so we'd need n plus 1 free lists, so that's 1 for each size. And then how this works, if you request some memory, so if they do not request a power of 2 size, we have to round it up. We'll have some internal fragmentation, but that's okay. In this case, we assume a power of 2 size request. So we'll search the free list for that exact size. If there is a block free, perfect, it's exactly what they requested. If it's not, well, we restrict our search a bit. We can just search the next power of 2 size up. So we could search for something twice as big, see if there's a free thing there. If there's nothing free there, we go up, search the next power of 2, so on and so forth until we finally find a free block of memory that can hold this request. If it's way too big, we recursively divide it in half each time until it's the correct size. All the other buddies would be inserted into the free list, so we'll have an example to see what that means. And then for deallocations, where you give memory back, well, we can coalesce. The whole idea here is we can coalesce 2 buddies together because they'll be contiguous based off how we split them off. So we can coalesce them back together, and we can recursively do this over and over again until we're finally done and we have the biggest free block we can get. So how this would look like anything with a white background, that is not free or anything, so it's just for illustrative purposes. So I'm assuming my buddy allocator in total is managing 256 bytes of memory. So right now I have a fulfilled allocation for red of size 32 and then a blue of size 64. So in order to fulfill this request, what this algorithm had to do was, well, 256 is too big, so it split it up into 228 byte blocks, and they are buddies of each other, but both of them had to get split off into 64 byte ones. Yeah?
Why do the splits have to be like equal size splits?
So the splits are equal size, so it's just really easy to coalesce them together. So here, if you know your buddy is free, you can immediately merge them back together, and that's why. So I can't immediately merge things that aren't buddies. So like this, if I freed the blue one, I couldn't merge it back together with this one because they're not buddies. So I make sure that it's all log n, right, because it's recursive. So it's just log n to coalesce things back together and also search. Yeah, so in this case, those 228 byte blocks, they're broken off into 264. Then this 64 one is broken off into two 32s. And then I use one of the 32s to fulfill that allocation. So I have one 32 byte block that is free, and then I have two 64 byte blocks that are free, and then one is used for the blue request. So everyone okay with that? So this is just where we are. So now, if we have someone request a malloc for 28 bytes, well, is 28 a power of 2? No. So in order to do this, I'd have to round up, right? What's the next power of 2 from 28? 32, right? So I'm going to lose 4 bytes due to internal fragmentation. That's fine. So in this case, if I round up to 32, and I look, do I have a 32 byte block free? I do, so I would immediately just put the allocation there and mark it as used. So now, if another request comes in for size 32, then, well, do I have any 32 byte blocks free? No, so I have to look up the next level. So do I have any 64 byte blocks free? Yes. So in this case, you probably just pick the first one. So I have to pick this first block, split it into 2. Then I use one of them for the 32 byte allocation, and then the other one goes back onto the free list. Yeah?
Wait, if 28, like size 28 less than 32, and we're splitting 64 into two 32s,
Yeah.
why can't we use the other 32 size memory that we do have to allocate the next 28, or to allocate 32? Like we're allocating now, so we first allocated 28, then we allocated 32, but we split it 60, like a block of 64 into two 32s. Why can't we use both of them for each allocation?
So we're assuming the allocations come in order. So this one came in first, right? So 28 came in, I rounded up to 32, and I just directly used this block.
Okay.
So then,
What about the block, like the red one? Like what was that for?
so the red one is an allocation before.
Okay.
So I assume someone already used it. So I can't move it or do anything. So any of the colored blocks are allocation requests that I can't move. So I already allocated it. Yeah. So that's why I had to split this one. So I have no 32 byte ones free right now. So I have to pick one to split. So let's say I split this one. The allocation comes in here, and then I would add a new 32 back onto the free list. So my free list now has currently one 32 byte block free, one 64 byte block free. So if I free this blue allocation, what happens? Yeah.
They merge and form one big 128 block.
Yeah, so this blue allocation, if it's freed, as part of freeing, it'd be like, hey, buddy, are you free? And then its buddy is free, so they will merge and become one. Sounds weird. So they become one. Nope, got weirder. So they merge together and become one free 128 byte block. So this is what it would look like after freeing it. And then now I can handle an allocation request of size 128. So everyone okay with that? Fun. Some variant of asking what happens on an allocation request and stuff. Come on the final, you can do it. Perfect, yeah.
What if you use like the third 64 block and then you want to allocate at 128?
Yeah, so if I went here and I split the other one, so this one was free and then this one was split, so we had a 32 and a free 32 here, then I just can't do it, right? If a bigger request comes in, not contiguous, can't do it. So I like the way you're thinking. It's almost like that's something that's on the exam. See, you could have written the exam. All right, so everyone okay with the buddy allocator? Sometimes when I make an exam, I talk too much, so I should probably just shut up. Yeah?
Just to be clear, in this situation, like just how it is, if you want to allocate like 130 bytes, it wouldn't work even though the 32 is like right next to the 128?
Yep. Yeah, so in this case, if I ask for, I don't know, a weird amount like 130, you might be like, hey, it's actually contiguous, I could do it, but the algorithm, it would add way too many complications. It's trying to be as simple. If you do that and cross boundaries, you've broken all the kind of rules. So then it can like immediately coalesce it, and then it's on a different buddy, and it just gets kind of weird. So they wouldn't do that to make the algorithm a lot simpler. All right, so buddy allocators, they are actually used in the Linux kernel quite a bit because they have several advantages over the default free list implementation. So it's fast and pretty simple compared to like the general dynamic memory allocation. Doesn't have to search the list. Has multiple lists, but only has to search is an element there or not. Never has to search the entire list. Worst case is I have to check the list at each level, but logarithmic, not that bad. Also avoids external fragmentation, more or less, not completely, but mostly by keeping things contiguous as much as it can. But the disadvantages is there's going to be some internal fragmentation if the user does not request a power of 2, because we have to round it up. If you're the Linux kernel and you're the only one using it, well, you're probably using powers of 2 anyways, so that's not much of a disadvantage. So that's why they would use something like that. The other option is our slab allocators that take advantage of fixed sized allocation. So you're allocating things that are all of the same size. So what you can do in this case, either manually or it might be an optimization in the memory allocator itself, is, well, you can just use a big region of memory for all objects of the same size. Basically, all you need is an array or a bitmap if you're doing Lab 6 to keep track of whether or not something is allocated. Since they're all the same size, you treat memory as just a big array and just keep track of whether that array slot is used or not, and it's a lot easier. So this prevents internal fragmentation. If everything is the exact same size, we don't have to worry about it. So how it works, basically a cache of slots, or you can think of it as elements of an array. So each allocation has like a slab of slots, that array, and then instead of a linked list, we have a bitmap to keep track of whether or not each index is free or allocated. So there is a mapping. Bit 0 would correspond to index 0, bit 1 would correspond to index 1, so on and so forth. So for allocations, it's really easy. You just search the bitmap for a single 0 bit and then figure out what index that corresponds to. Set that bit to 1 to indicate you've used that, and return basically a pointer to that element in the array, and you're done. For deallocations, if you want to be quick, you just clear the bit, you set the bit from 1 to 0, and you're done. And you can implement the idea of a slab on top of a buddy allocator if you want. So how that might work is, consider you have two size objects, an A and a B, where they're always the same size. Well, if you wanted to in your program, you might be like, well, it's not a power of 2, so maybe I ask the general malloc, maybe malloc's implemented with a buddy allocator, I ask it for a big block of memory, and I use that big block of memory as a slab. So I essentially use it as an array to hold the object. So each of these little slabs would be from the buddy allocator, so they would be a power of 2. And then on top of them, I would have my array of objects that are all the same size. So say this is 20. So maybe I can hold 4 in here and then have some space for a bitmap. And then maybe I ran out of space. I asked for some more memory from a buddy allocator, so I can fit another 4 here. And then similarly, maybe for B, they fit exactly 2 on a slab. Yeah? Oh, the red boxes just indicate like an actual allocation. So that's allocated, used by the program, and blank ones are free. Yeah?
So like slab A2 can like store 4 objects?
Yep.
Slab A?
Yeah. Yeah, so slab A2 can store 4 of A. Slab A1 can store 4 as well, but 2 are being used by the program right now. So 2 are free, 2 are allocated. Yeah. Yeah, this little tiny portion would be, if it's a really odd shape, that would just be unused. So that would be internal fragmentation. Yeah.
So sorry, I just add on to that point. So you said example, in this example, A has internal fragmentation. Is that because not all the objects are allocated, or is that because of the bit of space?
It's because of the bit of space. So like, assume object A is like a weird size, like 20. So if it was 20, every time I asked for memory from the buddy allocator, I'd be wasting, what, 12 bytes every single time, right? Because it would have to round up to 32. But instead, I could be like, okay, buddy allocator, just give me 100 or like 1,024 bytes, and I'll just stick a whole bunch of A's right beside each other, and then I can fit way more in, is basically the idea behind it. So you can mix and match, you can do whatever you want. So everyone all right with that? Yeah? So there's no coalescing here because it's just a bitmap of things, right? So you just flip it, they're all the same size. You don't have to coalesce anything. So this is also the bitmaps. You'll have them in lab 6 because you have a bitmap for blocks and also a bitmap for inodes. So that inode table is basically like a slab. You have a bitmap for the inodes, and an inode table, which is basically a big array. Yeah?
I have a question. So when we're splitting like the memory into powers of 2s,
Yep.
can we not take like, for example, one split of 32 and take, for example, another 32, split it, and take a part of that split and use like a combination of those splits to like insert, for example, A? Like if A is like, for example, 20, can we break up, for example?
Yeah, no, that would make things, I know where you're getting at. Like, yeah, I could split it and like have half, but that would make the algorithm way too complicated. So that would coalescing would get a lot harder then, because then you'd have to detect, oh, it was this part of a smaller part of a different block, and then you might have to merge 2 things from 2 different branches. So you could technically do that, but that would make it way more complicated. All right, everyone okay with this? All right, sweet, record. So even more memory allocation. So the kernel restricts the problem for better memory allocation implementations. You can restrict it by doing powers of 2. That would lead to something like the buddy allocator, or you could restrict it that you only deal with allocations of the exact same size. That means you can use something like a slab allocator, which, guess what, you're using for lab 6. So continue working on lab 6, and I will be around for any questions. But we're almost done. One more lecture of content, and then review, then exam, and hopefully we will all do fantastically. Yeah?
So sorry, didn't you, I don't know, maybe I misunderstood something. Didn't you say that we can use a body allocator with a slab allocator? Like,
Yeah, so like you could just, even in your own programs, you could just malloc a whole bunch of memory and then use that memory as a slab if you wanted to. It's just different ways to combine these techniques. Or you could just have a slab set aside. The whole idea is you can mix and match if you really wanted to. All right, another question? No? All right.